In this part of the lecture, we will discuss how the multi-bond graph for a rigid body can be constructed. Let's consider this rigid body. There is a frame B which is already fixed on it, and this rigid body can move in space. We also have an inertial frame here, frame 0, and we have got two representative points, point 1 and point 2 on this rigid body, and there are forces F1 and F2 shown to be acting on these points. So first of all, we'll begin with the kinematics of the rigid body. We'll establish a kinematic structure first, and then based on this kinematic structure, we'll obtain the dynamics. And it's a very simple approach. So the kinematic approach says that the velocity of the ith point observed and expressed in the frame 0 is equal to the velocity of the center of mass of the body observed and expressed in the frame 0 minus Ri with respect to the center of mass expressed in 0 cross the angular velocity of the body with respect to 0 expressed in the frame 0. So you can do this for all the points on this body, I equal to 1 to n. Now in this relationship, you have two important quantities. One is the velocity of the center of mass, which is shown here using this one junction. And the second one is the velocity, angular velocity of the body. The rate, angular velocity is the rate at which the orientation is changing, orientation of the frame B with respect to the frame 0. And here it's expressed in the frame 0. So we have the velocity of the point 1 is equal to the velocity of the center of mass minus Ri with respect to C expressed in the frame 0 cross the angular velocity of the body observed and expressed in the frame 0. We can do this for each of the points right up to the nth point. So you have the velocity of the nth point as equal to the velocity of the center of mass minus Rn with respect to the center of mass expressed in 0 cross the angular velocity of the body observed and expressed in the frame 0. So this is the kinematic structure on which we are now going to establish the dynamics. For this, we'll bring in the inertia of the rigid body. So the translational inertia, which is the mass of the rigid body, we assign it at the center of mass. So it moves with the velocity of the center of mass. So we assign an I element here representing the mass mb. Now the state associated with the I element is the momentum of the body B expressed in the frame 0. It's a product of the mass multiplied by the flow over here, which is the velocity of the center of mass observed and expressed in the frame 0. So we get the rate of change of this momentum is being caused by the resultant of these forces. So first you have the force 1, force 2 and so on right up to force n. So you have all these resultant forces being added up over here. So to obtain the resultant, all these forces being added up here to obtain the resultant, and they produce the change in the momentum, translational or linear momentum of the body. That is this equation. For the rotational side, we assign the rotary inertia of the body, which is given by the inertia tensor of the body about its center of mass expressed in the frame 0. And here the state associated with it is the angular momentum of the body with respect to the center of mass expressed in the frame 0. So the rate of change at which this angular momentum changes is caused by the minus r cross f. So here you have this change of momentum is equal to minus of minus, so it becomes just r cross f1. So this goes on right up to the nth, the moment due to the nth force about the center of mass of this body. So all these moments are added up vectorially. You may have moments additionally, torques, which are actually a combination of equal and opposite forces separated by distances. So the summation of those forces would be just 0, but there would be a moment of this couple which is given by the torque. Torque 1 may have more such torques acting, torque 1, torque 2, and so on. So the rate of change of the angular momentum of this body is given by the resultant of the moments of these forces plus the moments of the couples or the torques, summation of the torques over here. So here we have on the right hand side the translational motion of the rigid body, and on the left hand side we have the formulation of the rotary motion of the rigid body. So we began with the kinematic structure, and on this kinematic structure we assigned the inertias and we managed to get the complete formulation, and this becomes a single module for the dynamics of a rigid body. We can also assign the force of gravity over here. So we may construct, so we may have, we may place here a source of effort like this. This is a multi-bond. Here in this multi-bond graph, all these bonds have cardinality of 3. So they are all multi-bonds here. So here we are going to have the source of effort, which is the mass of the body multiplied by the acceleration vector due to gravity. So we'll take it as g. Yeah. So this will act here. So you will have the rate of change of the momentum being also caused additionally due to this weight of the body. So this is as far as the formulation of the rigid body, both the translation